Golden rule, you remember? I forgot it.
No, you are right now.
The Dirac delta function is already
Hello everyone. Welcome to this course. It's already launched on Jan 3rd week, I think Jan 21st. How are you all doing? Unfortunately, it's a two-way. Only you can chat and I can answer. And with this COVID protocols in the institute, we have to be with a mask on in the NPTEL SWAYAM studio. Okay, so what I will do is, you can start putting it on the chat, all your questions, and we will take it up one by one, pertinent to what has been taught. So far, I think 5 weeks have happened. So anything out of this lectures of these 5 weeks, I am not going to start giving lectures. It's already a 1 hour live session. So essentially, any doubts, anything which is missing, these are questions which I would like to answer during this live session. And I've also requested TA Pratibha to prepare a 10-minute slide on sudden and adiabatic approximations, as there was one tutorial on that and some students had some doubts. It's a different module. It's not really taught in the lecture, but it's good to know about when to apply those approximations. Okay. So Pratibha will present 10 to 15 minutes on it. Before we go on to Pratibha's presentation, I'll try and look at some of your questions. Okay. And then I will try to answer questions which are pertinent to this course. Okay. Pashupati Nath Datta has asked, please explain. Okay. Fermi golden rule I am not really teaching in this course. It will show up when you do time dependent perturbation theory, which will be the next level, the higher level after this quantum mechanics 1. By the way, the quantum mechanics 1 which I am teaching now essentially is to get acquainted with the Bra-Anket notation. Okay, and assumption is that you have seen Schrodinger equation, you have tried to solve Schrodinger equation, wave functions. This assumption I have already said in the preview before you could register, that this is what is the prerequisite. So many times in the lectures I do say that you would have seen it in the earlier course. But by that I mean the prerequisite which you have done, which you are supposed to have done. The wave function and Schrodinger equation is not the theme in this course, but for completeness, I am making sure that I am recapitulating many of them which you are supposed to know. So all the contents which you are supposed to know, I am doing it, recapitulating it for your own benefit, but it will not be done like the first course on Schrodinger equation. Okay, it will go, that part would have gone a little fast, assuming you know it and I am recapitulating it. I did see in forum some students asking what is that course and what is that course, but this course is not in the NPTEL, but you are supposed to have got a first exposure to wave mechanics, Schrodinger equation and wave function before coming into this course, where the focus is going to be on the Dirac bracket notation, and initially as a warm-up, whatever you have done in your earlier course or the prerequisite is being also explained in a couple of lectures. Okay, so that is one thing which I thought I should stress here. Yeah, so we'll come back to the couple of questions which everybody is putting. Let's go in the order in which students have asked. So Dirac delta function, it is something which, did we share a slide or something on Dirac delta function?
Yes, the potential and the voltage.
No, that is fine. But what I'm asking is, if they want to know what is the properties of Dirac delta function, that is not done, right? So what I will do is, it's a math component, the Dirac delta function. You must have got exposed during your mathematics course. If you have not done this, I will just share a small 2 or 3 page Dirac delta function file for you to know the formal definitions and the identities which a Dirac delta function should satisfy. Okay, so that's what is Pashupati. And degeneracy, I thought we have extensively done what is degeneracy when you go from 1D to 2D. 1D, you know, at least the bound states are non-degenerate. We have given a proof during the lectures that it has to be non-degenerate. But when we go to 2D, beyond the ground state, the higher excited states can be degenerate. Okay. By degenerate, what we mean is that the specific set of quantum numbers which describe a quantum state, they could be different, but those quantum states could have the same energy. Okay. So to explain that, let me just take the simple particle in a square box. Let me show it on the board. Okay, so I suppose you all can see the screen. So if you had a two-dimensional box, right, a square box where the potentials are infinity at the edges of the square box and the particle is inside. Okay, and we have written the wave function psi nx ny. This we have discussed in the lectures, right? And this wave function is going to give you energy, which is, so we will keep track of this nx and ny. So let me take the length of the box to be L, square box. Okay, so this is the energy. So you can see that there is a different wave function. I can put this as ny and nx, xy. So the quantum number is interchanged. I have interchanged it, and you can get an energy which is, technically it should be and this is also same as this, right? You all agree? Same as this. Okay, so the energy is same, but the states are different. So you have this state and this state are two distinct states. Two distinct state, quantum states, but both of them share same energy eigenvalue. Okay, so this is what is important. So that is what you mean by degeneracy. Degeneracy means the quantum states are different, the wave functions psi n x ny and psi ny nx are different, but they share the same eigenvalue. So that is what is degeneracy. Dirac delta function I have already told you will share a file with all the identities. Elementary particles versus identical particles. Identical means a collection of electrons, collection of protons and so on. Elementary particles means the particles cannot be further broken down. See, you studied in your school and early years of your college that you have every object including us is made of molecules. Molecules is broken down into atoms. Atom has inside an electron revolving inside a nucleus, revolving around a nucleus. Nucleus has protons and neutrons. You know this. So you keep breaking it, right? So the atom is not fundamental. It is not elementary. You have atom is composed of electrons and then a heavy nucleus composed of protons and neutrons. Then you can ask, is electron elementary? Can you further break it? So far from the present day experiments, we know that electrons are the fundamental objects. We have not seen it to have any more structure in it. But protons and neutrons seems to have structure. If you try to find a magnetic moment for a neutron, it is assuming neutron is a neutral particle, and if it was elementary, you would have expected it to be zero, but it is not zero, which shows that it has some kind of a structure or distribution of some elementary particles inside the neutrons. Okay, so in that sense, elementary particles are the fundamental objects typically which we see, and then identical particles means similar looking. You can have a collection of protons, you can have a collection of electrons, so that electron 1 and electron 2 are identical. So that's different from elementary particles. Stark effect in quantum mechanics of hydrogen atom. So what is Stark effect? I'm sure you would have all learnt in some way or the other that you turn on an electric field and then start seeing what happens to the spectrum, energy spectrum, and you'll see that there will be some kind of a splitting. Okay, so I'm sure you would have seen this in some course. So Stark effect in quantum mechanics for hydrogen atom is where you start seeing that the degenerate levels. What is the degeneracy in the hydrogen atom? So the degeneracy in the hydrogen atom, if you don't include spin and if the principal quantum number is n, azimuthal quantum number takes values 0, 1 up to n minus 1, and the magnetic quantum number takes for every azimuthal quantum number n minus L to plus L. Further?
Please continue.
Where do I go below? Okay, so hydrogen atom we write psi n l ml, and we are just ignoring the spin to start with. You can include the spin later. So you know that the energy is only dependent on n, and that means that psi n l equal to 0 to n minus 1, and ml is from going from minus L to plus L. So these are all distinct different quantum states, but share the same energy eigenvalue En. Okay, how many of them are there? If you count, you will see that there are n squared quantum states with same energy. Okay, what is En? En also you know, it is minus 13.6 eV by n squared. Okay, so there are n squared quantum states with the same energy En. Okay, so this is what we mean by saying that you will have degenerate states, and then when you turn on electric field, what happens? You will have terms with the energies which were En here. So let's take a specific wave function psi n L equal to 1 and ml equal to 0, 1, minus 1. So what is the degeneracy here for n equal to 2? This particular state was 3 states possible. L equal to 1 will have ml is 0, 1 and minus 1. What will happen if you turn on the electric field? The levels will shift. Okay. So it will no longer be n squared degenerate, but some of the levels will start splitting when you turn on the electric field. So that is what happens in the experimental setup on the Stark effect, and we can also see that some of the levels which were degenerate here becomes non-degenerate when you turn on the electric field from this course. Okay. So this is what is a couple of, please explain potential barrier, important operators, in quantum mechanics in plasma physics, Fermi theory of beta decay and neutrino hypothesis, pi meson. Okay, so my suggestion is that let us just confine to the first 1 and 2. I would like you to explore plasma physics, because every field applies the tools, just like you learn alphabets in your kindergarten, then go on to constructing 3-letter word, 4-letter word in the first standard, second standard. So students who are interested in particle physics can get to understand using the tools of 1 and 2 to understand point 4 of Fermi-Dirac, Fermi theory of beta decay, neutrino hypothesis, pi meson. Students who want to get into plasma physics can understand what is the notation. So this course is mainly to give you the alphabet tools, okay, with little applications. But if I start getting on to every application in every field, then it becomes, too, with this 12 weeks it cannot be done. Okay, so please understand, whatever tools we are saying, you can start trying to find the connections with what you will be doing or already doing in your specialized courses. Okay, so potential barrier, I'm sure I have explained potential well, potential barrier. So I'll explain this again. Important operators, of course, there are all the operators which you can construct using position and momentum are all important operators, right? Position and momentum will give you, R cross P will give you angular momentum. Position operator, square of the position operator, momentum operator. If you ask dipole moment, what is dipole moment? If you had a charge Q, Q times R vector is what you will have called it as a dipole moment. So dipole moment is also an important operator. Everything which you know as observables in the lab, you can associate the operator form for it in quantum mechanics, including in plasma physics. Whatever operators or whatever observables are seen, you can associate the operators. Okay, so potential barrier. So barrier means what? Suppose I move with an energy E, okay, and this is potential energy, let's say at x equal to x naught. Suddenly there is a big hill, okay, and you have only this much total energy with which you are moving. Okay, if you put this to be equal to 0, then you know that your energy is kinetic energy. Okay. So to climb that hill, you need to climb that hill. That is what we mean by a potential barrier. Unlike the other case where you can have the same situation where suddenly there is a pit. So you have an energy E and there is a well, and if I write V naught, you should remember from this axis, this is V equal to 0, then V naught is negative. Okay. So this is what is the potential well, and this is like the potential barrier. And important operators, I already said, you can look at position operator in one dimension, momentum operator in one dimension. You can have in 3 dimension a radial vector, then you can try to do r cross p, which is your angular momentum operator. So these are all important operators in quantum mechanics. And start listing it. Okay, so dipole moment is q times r hat is a dipole moment. This is also an important operator. Many times you look for whether there is a transition from one energy state to another energy state due to a dipole moment operator. Okay. So these are like finding the matrix elements of an initial state, and then a dipole moment operator and a final state, then the transition from an initial state to a final state mediated by a dipole moment operator. If this is not equal to 0, you say that the transition is possible from initial state to final state. If this turns out to be 0, then there is no such transitions. Okay. So this is what we need to know. And mesons, Fermi theory of decay, beta decay, everything I'll leave it here because it's not really pertinent to this course. And if you are interested, I'm sure in a nuclear physics course in NPTEL or an elementary particle physics course, it will be available, and of course we can answer you privately if you have any specific questions, but let me focus here in the live session pertinent to the course. Okay, Pashupati. So the next student Anand Badal has asked, I want to understand why and how a mixed state collapses to one of the eigenstates upon measurement. Okay, so this is one of the postulates. There are many things in quantum mechanics which is completely counterintuitive. And what is happening is that if you try to measure, whenever you try to measure, it is going to fall into one of the eigenstates of that operator. Okay, so this is something which is always happening. So that is why even in the Stern-Gerlach experiment, this is seen. If you try to measure the x component of the spin, then it collapses into one of the eigenstates. If you put a filter to get half h cross, then you get the half h cross probability, and then you again do an sy or an sz. So these have been experimentally validated. Now you take it as a postulate, okay, that any arbitrary state can be written as a linear combinations of the eigenstates of an observable. When you try to measure, it will collapse to one of the eigenstates. So if you had identically prepared, let's say 100 identically prepared such mixed state, every student is sitting with, there are 100 students, each one is sitting with it identically, it will collapse into one of the eigenstate. Which eigenstate you can't also predict. So out of the 100, you can see probabilistically. You cannot deterministically say that it will collapse only to this eigenstate. It will probabilistically collapse into those eigenstates is all you can say. But it will definitely collapse into one of the eigenstates because measurement will only pull out a number which is associated with the eigenstate of that operator. Okay. So take it as a statement and proceed, and experimentally it has been validated. Harmukpreet Singh, my question is about wave nature and wave packet of electron. Is electron consists of multiple waves? Can you further explain about its wave packet nature? Okay. So what is a wave packet? Wave packet is a superposition of waves. Okay, so this is one thing which we should know. Each wave will have a definite wavelength. Okay, a wave packet is a superposition. So delta lambda, will it be 0 or non-zero? It will not be 0 for this case. The uncertainty in wavelength, it's not having specific lambda. The wave packet is a superposition of all possible lambdas. So delta lambda is going to be imprecise. If you try to find specifically the uncertainty, this is equivalent to, because of de Broglie hypothesis, this implies delta P is also not 0. Okay. There is a momentum uncertainty on a wave packet. But when you superpose all of them, all possible wavelengths if you superpose, you can in fact say delta P is really large, and the corresponding localization of the wave packet. I'm sure you would have done if you had taken two waves. If you had two waves, this is with wavelength lambda 1, another wave which is with wavelength lambda 2. When you try to superpose them, you can see a region of larger amplitudes, you can see a region of smaller amplitudes, and if you keep composing, if you try to superpose lambda 1, lambda 2, lambda 3, in fact you take lambda if you take lambda, then lambda plus delta lambda, okay, delta lambda, lambda plus 2 delta lambda, and so on. If you superpose all possible wavelengths, what you will end up is getting some kind of a region, and then things are all. So this is what happens for a wave packet. If you superpose all possible wavelengths, then there will be a region where there is high probability of finding the superposed wave packet. And if this region is really small, if I say that delta x, so this is the plot on psi of x versus x. Delta x is small, which means you can locate the wave packet. What do you mean by locating the wave packet? You cannot predict the wavelength of the wave packet because wavelength is all possibilities from lambda, lambda plus delta lambda and so on. But you can locate the wave packet, which means the wave packet, the closest description of the wave packet is particle nature. Okay. If it is almost zero, you say that the wave packet will have a group velocity, and that group velocity is what we call it as a particle velocity. I hope that answers your question. So electron, if you treat it like a particle, you can treat it like a superposition of all possible waves. If you treat it like a wave, it is a single wave with unique de Broglie wavelength. So a wave packet is the closest to explaining particle nature of electron. Is de Broglie wave consists of single wave or multiple? Typically when I say de Broglie wavelength, if I say it has a de Broglie wavelength, I give a momentum and I find the de Broglie wavelength, which means it will have a single wave. Okay. So it depends also on the experiments. If you are going to look at particle interpretation, you have to treat it like it is not a unique wavelength, but it's a superposition of all the possible waves. Okay. Yeah. More questions are there, or that's it? More questions? Is it not seen there?
Nothing more.
Why is it there? We've seen already maybe. Hmm? Where is that? Top chat. Well, we went it to the bottom. Okay. Klebsch-Gordon we have still not started. I don't know why you are jumping to all those other lectures. But please explain Klebsch-Gordon coefficient. The way I would say is that when you compose two distinct particles or two distinct spin-half combination, you can start seeing that this composition and writing the states will require Klebsch-Gordon. Let us wait till the lectures are over. Maybe in the next live session we will take it up. How can we say that single valuedness of a wave function in angular coordinate leads to only integers in magnetic quantum number? This is very simple. Okay. So let's take a particle on a simple circle. Okay. Circle can be given by, so it is circle of common radius r. So different points will correspond to theta 1, theta 2 and so on. When you come back here, it has to be, if it was originally theta here, it should be theta plus 2 pi, right? If you come back to this point, let's say a point P, initially it was theta. When you go one round circle and come back, it is the same point P, but the angular coordinate has done one rotation, so it comes to theta plus 2 pi. But it's the same point. What is required? Single valuedness means what? Psi worked out at the point P, which is taken to be theta, should be same as psi at the point P, which is written as theta plus 2 pi. This is what is single valuedness. Why theta plus 2 pi? Any integral multiple of 2 pi. If you put this condition on your angular coordinate in the hydrogen atom, it will force that the corresponding quantum number has to be an integer. So I leave it you to do this. We have done particle in a box, in a one-dimensional bomb. Do a particle on a circle. Okay. Take the particle to move only on the circle of constant radius r, capital R, and see what wave function you get, and you impose this periodicity. If you impose this periodicity, then you will see how your n has to be an integer. Okay. So please check this out, and that will tell you what is single valuedness, because the point P is the same when you go in a circle many times. When you go 2 times, you have traveled theta plus 4 pi. But the wave function at that specific point on the circle has to be same. So this is what is the condition we have to put when you are trying to find the wave function which is single valued. Okay. So the next question, Suchit Prajapati. I want to ask, why does light show both particles and wavelength? That's the beauty, you know. We are all so used to treating light as a wave. We would have missed many of the processes, right? Black body radiation, the black body spectrum, which fit very well with the Planck's hypothesis. Photoelectric effect, Einstein's important contribution, which requires it to be having the quanta which is photons. These things looks completely counterintuitive. But if you take this counterintuitive proposal, the experimental data of Compton scattering, photoelectric effect, black body radiations can be explained. So that's why in certain situations, most of the things which you have learned, interference, diffraction of light, are all wave nature. But you have not seen that particle nature is important to explain photoelectric effect, Compton scattering. So in general, light also shows both the dual natures, both the natures. You can't simultaneously tap both wave as well as particle nature, but if you try to probe in the particle information, you will get particle information. If you try to probe in the light information, like do an interference experiment, you will get the wave nature information. Okay, someone has already said that the prerequisites which I mentioned is already taught by Brand Carlson from Carthage College. So I need to check this, but you can also take a look at it. Okay. You note it down and check it out also. Carthage College, where is it? I don't know. See, many of these sites where they mention, you need to also check out the authenticity. So we'll try and check it out and we'll update you on the forum. Okay. So just hold on for a day and we will update you. But Alagappan says that it is, he's been following, looks like. But anyway, you take a look at it. Okay, the hydrogen fine structures, I'm not going to take it up here. You need to go beyond non-relativistic quantum mechanics, and the crux of this course is non-relativistic quantum mechanics, not relativistic quantum mechanics. But you will learn at some point those fine structure details if you are doing a relativistic quantum mechanics. So some students are saying screen not visible, you can't see screen, everything. They are okay now? Looks like. Okay. How to visualize complex numbers? Complex numbers are presented in 2D graph, but if we have 3D, how can we visualize? Should we view it as like a single dimension or axis as one? Okay, so Complex numbers are complex numbers are not what you see in your experimental lab or anything. Okay, it's just a technique which helps us to do the computation much more elegantly. A huge machinery of complex analysis helps you to do even simple integrations which may look very complicated. If you do a contour integration, you can get the real part of that complex integration very beautifully. Okay, so that's one thing. So in that sense, complex numbers as a tool is really useful. And the other thing is that you can write, xy plane, you can write x plus iy as a complex number and start looking at, if I take x and y and rotate it to x prime, y prime by rotation by an angle theta, you would have written it by the conventional rotation matrix, which is cos theta, sin theta, minus sin theta, cos theta on xy to give you x prime, y prime. Is that right? But if you want to redo things on the complex plane, what happens there? Z goes to Z prime, and that Z prime will be just e to the I theta times Z. It's just a rotation which is given by a phase path. So these are couple of ways in which a 2D graph can be viewed. In fact, any even dimensional space, you can try to do it as a, if you had 4-dimensional space, you can write x plus iy for z1 and another complex coordinate for the other two coordinates. So these are all techniques to simplify the computation. Ultimately, the results which can be compared, you will not get complex numbers because they are not measurable in the lab. Ultimately, we extract the physics which can be compared with the experiments, and these tools are useful. Okay. Okay. Quantum numbers, how do we find dual of a ket? I thought dual of a ket we have extensively discussed, right? One of the important thing is the coefficients also becomes complex conjugate. Typically the Hilbert space will be not a real vector space, but you will have it to be a complex vector space. So the coefficients, if you write it in terms of the basis vectors with coefficients, the dual of that state will be a bra, and the coefficients will also become complex conjugates. That is very important. Okay. Yeah, Stark effect and Zeeman effect have a similar set of properties. One is by turning on the electric field and the other one is turning on the magnetic field. Sujit Prajapati is again asking, my question is related to the creation of universe in Vedic cosmology. There are various particles. How is particles relevant to modern? I think the particles, elementary particles, are the fundamental objects based on which the whole world, universe, everything is being built up. To understand the quantum aspects, how it behaves in a microscopic world, is what we are trying to explain. Okay, so we are not really looking at many of these things which seems to be appearing in the fields like Vedic cosmology, but knowing these tools you can go and explore more on these Vedic cosmology and see whether there is connections. Okay, right now I am not going to relate these to other applications in other physics like plasma physics or particle physics or Vedic cosmology, but you are welcome to explore after learning the essential tools in this course. What is magnetostrict? I don't know. Learn with ma'am. Please tell me the use of magnetostrict. I don't know. Where did I use it? I don't know what you mean by this. Ma'am, about the Stern-Gerlach experiment you talked about in one of the lectures, can you throw some light on if I say the electron takes up upward spin or down spin because of the collapse due to the measurement. Yeah. So the collapse due to the measurement, it can either have probability, suppose the state had 75% probability of being in the up state and 25% in the down state. When you try to do the measurement by putting your magnetic field along the x direction, let's say, okay, it will collapse to either the up spin or the down spin with different energies. Okay. You can put filters to absorb, let's say the down spin I don't want, only the up spins I want. You can collimate it. So these are things which are being done in the Stern-Gerlach experiment. And then that state, when you put it through another magnetic field along z direction, you will get again both the components. You will have both up spin as well as down spins. Okay. So typically the splitting of an arbitrary eigenstate of Sx is a superposition of the eigenstates of Sz. So this is what I have been explaining in the lectures. So if you closely watch with the measurement, you will start seeing this superposition. Okay. Please stick to the topic, that would be great. He is answering the other person.
Yeah.
Yeah, this I have already explained the complex notation, and this is important if you want to extract the information which can be matched with the experiment. How did physicists come up with operators and their formula? Why do some kinetic energy Hamiltonian have complicated ones while others position, potential energy? I don't understand this. So it depends on the system, right? If you try and look at a two particle system, you have to write kinetic energy for the particle 1, kinetic energy for the particle 2. If you want to write the Hamiltonian, it is kinetic energy plus potential energy. So even the helium atom, if you take, you can write the Coulomb kind of potential due to one electron and Coulomb kind of potential for the other electron. But there is also an interaction between those two electrons, Coulomb kind of potential with the nucleus, right? But you can also have an interaction between the two electrons. So those are complicated situations. Solving a second order differential equation, Schrodinger equation, using such a complicated one is a tedious job. Okay? And this is what is the theme, how cleverly we can use these tools and get more information. I have tried to throw some light in my lectures, complicated looking potential energy, but actually you can do a coordinate transformation or combine and make a complete square. So these are ways in which you can solve the Schrodinger equation and find the energy spectrum and the wave function. Can we apply different conditions of potential barrier to the transparency of the material, as the bond energy is also kind of, yeah. So these are things which we need to try and see how to model them. Suppose you want to look at opaque material, which means, opaque means what? It is not going to be, you won't find the transmission coefficient basically, right? A translucent and transparent can have both transmission coefficient to be non-zero. So these are things which can be mimicked. Can you explain the wavelength is higher in Compton scattering, how the frequency and energy was? So wavelength, Compton scattering will give you a delta lambda, and that depends on the scattering angle and the Compton wavelength, right? And the Compton wavelength is dependent on what is the object. Suppose you had an electron, so your Compton wavelength will be inversely proportional to the mass of the electron. So you can determine what is the energy, incident energy, what is the frequency of the incident photon on when it undergoes Compton scattering with an electron. So this is a very simple, straightforward exercise to do it. Mano Mani, you can try it out. If you still face any problems, you can email and you can explain it. Okay, please explain ground state energy of the hydrogen atom and non-existence of electron in the nucleus. So I am not going to explain here, but if you do the solving the Schrodinger equation in r theta phi coordinates, try to find what is the eigen value. It turns out to give the ground state energy, which is minus 13.6 eV. Okay. Why electrons cannot exist inside the nucleus? I'll leave it you to do it. Assume it is there and try and find a contradiction with the kinetic energy, how you will get a contradiction for it, and then you will be able to understand why electron cannot be inside the nucleus. Can you explain little about phonons? Of course, phonons are like wave natures of the sound, but that is not what we are going to try and explain here. But any student who is doing condensed matter will start relating whatever tools I am teaching here in the phonon waves and so on. Okay. Can you explain how the wave function of particle in a ring with different values of quantum numbers are orthogonal? I'll leave it to you. You check it. Okay. It should happen that you should find different energy eigenstates to be orthogonal. So what exactly is photon? Photon is the particle description of your electromagnetic wave. Okay. You can treat electromagnetic wave, the particle nature is described by the photons. Like electron as particle, and you can look at the wave nature of electron as the de Broglie description. You can here treat photons as the particle manifestation of the electromagnetic wave. Wave function for particle in a ring, I am getting it to be. So please try it out, and maybe one or two in an assignment we can include and then explain some of them. Okay, so the entanglement also we'll do it at some point as a discussion, but what is happening is here I have, due to lack of time and also pertinent to only the contents of this 4 weeks or 5 weeks are over now, 5th week is going on. So I don't want to get on to this entanglement, but there is beautiful, the entanglement is itself a beautiful subject, and it would be nice if you can keep track of what is happening in the quantum entanglement. Some point I will try and see whether I can share some files or on the quantum entanglement. Can you explain what a coherent, it will come, let it come, and then we will talk about these coherent states. What is the basic difference in relativistic and non-relativistic? Of course you know it, relativistic energy momentum relation is Einstein's equation. Non-relativistic kinetic energy is taken to be p squared over 2m. That is not going to explain the relativistic aspect. Why is the spin of an electron assigned as half and not as 1? That's also a good point. The thing which is being done here is when you do a rotation by 2 pi, the wave function picks up a negative sign. Okay? The wave function picks up a negative sign, and that can be explained only if you have it to be half and not 1. Okay? So I am leaving it there, but we will come back to this. Okay? Or rotation of one electron around the second electron is like an exchange, and then you can see it by the two identical electrons. When you exchange, it has to pick up a negative sign. These things can be explained only if you give the electron to be a spin. So let me stop here. Is there any more questions? Yeah. So can you give them the presentation? What is the time? Yeah, just quickly go through it and then you can. Maybe you can come here and explain it on the file. It's a transition and then you can get to the file. So she will explain, Pratibha will explain the sudden and adiabatic briefly, and she will share the file in the forum. Okay. don't go too much into the details, but let them take a look at it, and then we can. So this is really not going to be on their exam module or courses, but it's good to know.
Yeah. Okay. So hello everyone. I'm Pratibha, the TA for this course, and I'm going to discuss this interesting topic in quantum mechanics, that is sudden and adiabatic approximations in quantum mechanics. A brief discussion on this was requested by one of the learners, so we decided to have it here in the live session. So yeah. Okay, so usually this is discussed under perturbation theory.
So use the mouse. Yes. You can do it slowly.
Yeah. So okay, yeah. But today we will use a different approach to understand this with the content that you have learned so far in the last few weeks. So yeah, let's get started. Okay, so till now you have focused only on the systems where the Hamiltonian was time independent, like particle in a box, finite potential well, delta potential, all these things. Here the potential itself was time independent. So you can solve the Schrödinger equation in a easier manner by using the separation of variables and then expressing the system psi as a linear superposition of the Eigen states of the Hamiltonians. But there are many phenomena in nature which are governed by time dependent Hamiltonians. And for example, interacting particles, interaction of atoms with electromagnetic radiation, and so on. So in general, solving the Schrödinger equation for these Hamiltonians is difficult, and often we consider approximate solutions while dealing with such systems. Here we will consider two situations where the Hamiltonian has extreme time dependence. First one is where the Hamiltonian changes rapidly in a very short period of time, that is considered under the sudden approximation, and second is where the Hamiltonian changes very slowly and continuously, that is considered under the adiabatic approximation. Okay, so the condition for sudden approximation is that when the Hamiltonian changes rapidly in a very short interval of time, the state of the system psi remains unchanged. It means consider that the wave function psi has some inertia and it doesn't actually get time to adapt or respond to the change when the Hamiltonian changes very quickly in a very short interval of time.
Krista, you can kind of tell them that they can see these slides. We will share it in the forum, and you can show the pictorial form of your.
Yeah, sure. Okay, so you can go through these slides to see how we can use the approximation method to solve this the time dependent Schrödinger equation. We will share the slides in the forum as well. So to be very short, I'll show you pictorially what happens just to compare what happens in sudden and adiabatic approximation. So consider this is the initial state where the particle is in its ground state, and suppose first let's jump to the sudden approximation. This is the case of sudden approximation. So suppose the wall of this wall at A is moved very quickly to 2A, that is the length now becomes 2A. So the wave function, the psi doesn't get any time to be dragged or respond to the change. So for that the wave function is continuous till A, and from A to 2A psi becomes 0. But in case of adiabatic expansion, when the wall from A to 2A is dragged very slowly and continuously, the wave function also gets dragged along with the wall. That is, the wave function is continuous all the way from 0 to 2A. So you can see how this is different. Like if you try to find out the wave function anywhere between A to 2A, you will find the same wave function. But in case of sudden, A to 2A, psi becomes 0. And for further reading, there is this interesting paper, American Journal of Physics. You can just copy this link and paste it. And then there is an interesting paper by D.N. Pinder, that is the contracting square quantum well. The gist of the paper is that adiabatic approximation can be used for both expansion and contraction, that is both expanding and contracting wells, whereas sudden approximation is appropriate only for expansion but not for contraction. So yeah, that's all about in very short about sudden and adiabatic approximation, and you can go through the slides and this link for further reading. That's it.
So there's
Thank
one
you.
final question which we end with this. Vardhan is asking, is there any way I can access past question papers? I don't know. That depends on the NPTEL team. I'll figure it out. Okay? Yeah. Thank you for all of you making time to be present here to ask your questions. And of course, in the forum we'll keep answering. So please post your questions but please be, keep working on watching the videos and the lectures, and please be active, and we will have every month one live session so that you can clarify all your doubts. Okay, see you, bye bye. Yeah, how short a time, those conditions are already Spandan, how short a time needs to be for the change to be sudden? The file has what is the short time, what is the condition, what is the Hamiltonian dependence, etc. And paper, American journal paper actually shows contraction cannot be done suddenly. Okay. Yeah.
Thank you.
Okay. See you. This is quantum mechanics. Yeah, group theory.
This one.
No, that is quantum mechanics. 4 to 5, 5 to 6 was. But it said group theory at some point here.